We're carrying on in our discussion, and today we're going to look at one of the simplest models of a solid, and that is the Sommerfeld free electron gas. Along the way, we're going to introduce something called K-space, which will be a useful concept that you'll use in other areas of physics, and an application of this will be what's called the degeneracy pressure. So this theory is a theory in condensed matter physics. So we're getting to the point now in quantum mechanics where we've learned some basic quantum mechanics and we can start applying it to different situations. And condensed matter physics is the field of physics that deals with macroscopic and microscopic physical properties of the condensed phases of matter. So a couple things about that. So first of all, it deals with things that large number of condensed particles. So every day you got like solids and liquids. And in my mind, I sort of think of condensed matter physics. It used to be called solid state physics, and so I can imagine like the first people in this field were trying to figure out why do some materials conduct electricity and some don't, for example. So the sort of study of large numbers of particles as they come together, and some of the sort of more exotic cases these days. You got things like Bose-Einstein condensates, superfluids. So here's a couple pictures. So here's maybe one of the first things people looked at were solids. Here's a bunch of atoms coming together to form a solid. Here's something that you can talk in more advanced classes, superfluid, which is an example of a Bose-Einstein condensate, where some really interesting things can happen. And here is sort of the one of the hot condensed matter systems, which would be graphene, which is two-dimensional carbon, which has some really exciting qualities and characteristics to it, and so is an open field of research that people are studying right now. So this will be our first discussion of a type of a theory from condensed matter physics. And here's a quote from Lorentz. So in a theory which has given results like these, there certainly must be a great deal of truth. So in condensed matter physics, there's generally so many particles, right, where we can't even come close to trying to account for all of them and solve this system exactly. And so what we're looking for models, all right, that are going to be approximations, but hopefully, as in the quote here, bring along a little bit of truth as well, and maybe, if we're lucky, a great deal of truth. And just as a rule of thumb, we're going to be dealing with, Avogadro's number of particles. So we're dealing with macroscopic things now. So 10 to the 23 particles. So what we're looking at now is called the free electron gas model, and it's a three-dimensional analog to the infinite square well. So that's nice because we're pretty familiar with the infinite square well. Again, it's a rudimentary model of a solid. And in this model, electrons feel no forces except that of the confining walls. So a couple things that we're not including any kind of electron nucleus interaction, and we're not including any kind of electron-electron interaction. So this is a really bare bones model, but still, surprisingly, it has much use, and it's something that you can build upon. So our potential is a three-dimensional potential, and just like, again, the three-dimensional analog to the infinite square well, the potential is zero inside the region that we're talking about, and then it's infinite outside of that. So basically, there's no probability for the particles to be outside of this region. And if we were to sort of just make a little quick graph of what we're talking about here. So let's make a three-dimensional picture. Here's our typical X, Y, Z axes. And so we're going to do this for some general shape, like so. And so in the three sort of different dimensions, so like this length right over here would be our length in the Y direction. This length right here would be our length in the X direction. And that length right there would be our length in the Z direction. And so we make, some kind of a three-dimensional shape like this. And so we're basically trying to model this solid. And so we're going to say that the electrons, again, are feeling this potential. So there's zero potential when they're inside the box, infinite outside. So they're basically trapped inside the confining walls. And so what does our equation look like? Well, of course, we start with our Schrodinger equation. This is in three dimensions. Okay, we're going to do this in Cartesian coordinates because our shape lends itself to that. So that's really a nice, easy way to do it. And so we're going to assume, like we typically do, that we have a separable solution of three different functions. One function of only x, one function of only y, one function of only z. So we've done separable stuff before, and so let's just go through this. And so our Hamiltonian ends up being our usual constants, and then our derivatives, our spatial derivatives, and of course the time-independent Schrodinger equation, which is what we're using, the three-dimensional time-independent Schrodinger equation, is a eigenvalue equation, and so it's and again we're also saying that the potential is equal to 0, so we don't have the potential term, and so we have basically our kinetic energy term times our wave function equals energy times our wave function. And so what we typically do in a case like this, right, is we take both sides and we divide by that wave function. So we divide by the wave function. So on this end, basically the wave function, 3 components will disappear. On this end, we'll find that basically the parts that aren't being differentiated will disappear. So like for instance, this is the first term, and so this is our constant times the second derivative with respect to x, and so that only affects this guy. And so the y and z come through when we do that, and then this is the second derivative, and then of course with the other two, when we do that, this side comes out the x and the z, and this is the x and the y. And so when we do divide by this whole wave function, what happens is over here, like in this case, the y and the z cancel, and I'm left with 1 over x for the x term. For the y term, similarly, the x and the z cancel, I'm left with 1 over y, and then here the x and the y cancel, I'm left with 1 over z. And so we get the situation that arises a lot where we have, in this case now, 3 terms. Okay, so this thing plus this thing plus this thing equals a constant. And since these are all 3 different functions of one variable, so it's basically I got one function of x plus some function of y plus some function, we'll call it h of z equals e, right? And so the way that this works out is this, the only way this can be true is if all 3 of these functions equal a constant. So we'll call the constant to be ex, ey, and ez. So again, these are the 3 constants, ex, ey, and ez, and those will equal the total energy. So then what we end up with are 3 infinite square well equations. And so just like we would have done in chapter 2, and so we go back and we see then that what our solutions will be. So for instance, the solution for this x equation is going to look something kind of like this here. Again, definitely a good idea to go back and check over this and make sure remember all this. So the actual wave function, so the big difference here is that now each one of these directions has a different length associated with it. So basically that length, right, we're setting up the boundary conditions on that length, and each side has its own quantum number. So instead of having n, we have nx. Instead of having whatever this length used to be a, now it's Lx. And so the energy that we were calling, say, Ex, will now look something kind of like this here. Again, this is exactly the same form that we had before dealing with the infinite square well. It's just that now we have 3 different dimensions to deal with. And so if you remember, the format of our wave equation from over here, right, is basically these 3 functions multiplied by each other, and our total energy, we can call this the total energy, is the sum of these 3 different energy pieces. And so when we write this out, this here will be, again, our wave function, right, our energy eigenstates for this system. And so this would be the 3 constants sort of multiplied together from the 3 different pieces. And here's the 3 different pieces set up like that. And then down here, our total energy will end up looking like this here. And so it's a little bit tricky because of these different directions here. But a way to simplify it is to do this in terms of what we call this k vector. And so this is going to lead us into this idea of k space. And so the k vector is defined this way here. And it's basically just a sum here. And what this essentially is it's a way to represent the 3 quantum numbers, nx, ny, and nz. And we're going to see how this shapes up as we move on here. So this is our way to represent this k squared. So the k squared, you can think about it as basically being a sum of these terms that really just are going to be telling us about the quantum number in the three directions. So again, we have, in a sense, three different infinite square wells, and so you can have all three of these have different quantum numbers, where again these n's are defined as being 1, 2, 3, 4, so on and so forth, like that. And so that's going to define our system. And so when we talk about our system for a particular electron, right, it's going to basically be in some to sort of specify the system, we've got to specify nx, ny, and nz. Okay, so if you tell me those three numbers, I know exactly what my wave function is, and I know exactly what my energy is from that. And so that's where our starting point now. Yes, this is our starting point, and again, oh, look here, just be clear, these should be pi squared, these two pieces here. Okay, so here's a question just to help us better understand the system. And so let's put one electron into a cubical box. And so that makes this a little bit easier. We've been doing this for the general case where the three sides can be different. Let's assume they're all the same. So if that's true, then this energy equation simplifies a little bit. We can pull the pi squared and the L squared out and then just write it in terms of, again, these three quantum numbers. And write it in terms of this here. What is the degeneracy of the first excited state? Okay, so basically, how many different first excited states do we have? Think about this, and we'll talk about it. Okay, so hopefully you got 3 for the degeneracy of the excited state. And so again, let's look at this here for our system. So the energy total, we're just calling this E0 times the square of these 3 quantum numbers. And again, these quantum numbers are just the quantum numbers for the infinite square well. And so for the ground state, that would be the case. So the ground state, I'm going to write these sort of in a little vector here where we write the 3 components. And so this is our sort of general case. So the ground state would be where these are all 1. And of course, so the energy for the ground state would just be where these are all 1. So it would be 3 E0. Now the first excited state, right? So that would be a case, now that would basically be where one of these is 2. And so hopefully you can see that, you know, there's 3 ways to do that, and that's basically by having the 2 be in the different place. So 1, 2, 3. So the degeneracy is 3, and then the energy for the, we'll call it the first excited state, then would be E0. And again, it doesn't matter, but one of these should be 2, so you get 4 plus 1 plus 1, and so you get 6 E0. All right, so just again, trying to get a better sense of what this looks like. So for our first discussion of K-space, I usually like to start off with two-dimensional K-space. It's, you know, it's got the same flavor, it's just a little bit simpler to visualize. And so here's our K-space. We've got, you know, the KY dimension and the KX dimension, and they're in units of pi over the length for each of the sides. There's like pi over Lx, 2 pi over Lx, so on and so forth. And so again, the energy for our system, when it's in 2 dimensions, looks like this. And so basically the energy is characterized by nx and ny. And so if you look over here, I've just circled 2 points. So each little point on this K-space represents a particular state that the electron could be in. Here's nx1 and ny3, and over here is nx3, ny1. And so each little point tells you one of those. And if you look here, you can draw, you know, you can think about this arrow as being like the K arrow. And so here's the K arrow for this particular case here. And if you look at that, the length of that K arrow in terms of this space would be the number nx squared, pi squared, lx squared, plus the same one for the ny. And so this gives us sort of a geometrical way to visualize this. Again, we want to emphasize that this is not real space. This is a K-space, so it's not a physical space. You know, a kind of analogy would be like Hilbert space, right? We're talking about Hilbert space with vectors, and we use a lot of the same concepts that we use for real space vectors, but it's not a real space. It's the same sort of thing here. It just can be a really nice way to visualize. And so what we're going to do a lot of is basically trying to figure out, you know, if we say put 10 electrons into this system, what is the state that we're talking about, right? And so if you think about this, well, for each of these states, we can put 2 electrons, one spin up and one spin down because of the Pauli principle. So if we do have like, whatever, we just sort of can populate states by just sort of putting them in here like this. But we can also use the power of this space. It'll be much more important for much larger numbers. And what we can do there is kind of make a geometrical argument. We can say, well, if we're going to fill this space up here, right, we can make some sort of a shape like this. And then this we'll call the vector, we usually call this kf for k Fermi. And so this is a vector on this, and it's basically pointing to a place here where maybe the maximum state is going to be, the maximum energetic state. And so as we fill in the electrons, they're basically going to fill in like this, because this length, this vector k, right, tells us essentially how energetic that particular state is, because I can replace this energy here as h bar squared k squared over 2m, where this is the length of that k. And so if I pick some point, the more energy, the bigger k. And so what we're going to end up doing is sort of making these geometrical shapes and then assuming, okay, so if I can sort of fill in all of this with a particular amount of electrons, right? And then I can sort of tell the most energetic state I have a little bit easier than kind of putting them in one at a time. And so when you get to really large numbers, if you draw like a shape like this, it's going to give you a really good approximation to sort of your most energetic state, which is going to be our goal now, is to find the most energetic state, which we call the Fermi energy, E sub f. And so we're going to go through and do that right now. And so this then would be our three-dimensional version of our K space. So again, it gets a little bit busier, but you can, the same sort of idea, imagine here's a little box bounded by the first kind of dimensions. And so this right here, this would be the point in our three-dimensional K space of 1, 1, 1, where again we're doing this in terms of like ny, nx, ny, and nz, like so. And so this would be our cube, and this cube, if you blew up this cube, the volume of this cube, so I'm going to claim that this is the volume, again, in K space, that holds one state. Kind of we did the area in the 2 dimensions, and so that would be pi over Lx, pi over Ly, pi over Lz. And so out of that we get pi cubed over all those 3 guys, which again, this is the real confusing part, and apologies for the way they do this, but they call this the volume in real space. And so the volume of a cube, which is again the volume that for one space in this K space, is this here, again in a really analogous situation. And so like I was saying before, in a case where you're dealing with 1 or 2 electrons, K space isn't really advantageous. But in a situation like this, where basically we're going to fill this box with like 10 to the 23 electrons, it's going to be much nicer to think about it this way. And you can kind of imagine the other thing that we got going on is the Pauli exclusion principle. So basically we can fit 2 electrons into every one of these states. And so what happens is when we put a whole bunch into there, right, and then sort of just have them fill this up, it's going to fill up a rather large volume of this picture. And in fact, that's where you get this sort of picture like the book holds, where you basically fill in all these guys, and what happens is you get this thing here, which is like 1/8 the volume of a sphere. So you can imagine if you sort of fill every dot with 2 electrons, 10 to the 23 or whatever it is, a huge number, you're going to get a really big volume in this K space. And so it's just easier to kind of visualize it this way than it would be to sort of count each of these little things individually. All right, so our goal right now is we want to take this K space and figure out basically when we put in all of our electrons, how big is it going to be? And we're going to be able to use that to hopefully find ourselves some information. So one thing I'll point out, this is a picture from the text, and so you can think about this K vector as emanating from the origin and going to the surface of this sphere. So basically our idea is we're going to fill in 2 electrons into every spot, 2 because you can put a spin up and a spin down by the Pauli exclusion principle, right? And we're going to fill it up until it fills up this volume of K. And the thing is, our number is going to be so big that this thing is going to look and approximate the surface of a sphere very well. And so this is the surface of the sphere in our K space. And so what we do is we say 1/8. And why do we do 1/8? Well, again, our states are only positive values in this K space. And so it's only going to be 1/8 of this sort of possible sphere. And so 4/3 pi, we're going to call it K cubed. And we actually call this K sub F. We'll see that that's for Fermi. And we're going to equal that to basically the total volume that we're going to be putting in for our individual particles. And so what we do is we say, well, there's going to be n atoms in this material. For each atom, we're going to say that it adds d electrons. Typically that's a small number. Usually it's 1. It could be 2. And we're going to multiply that by the total volume of our K space here. And so this is the volume we expect this to take. And the one last thing we put in is a factor of 2. Again, because of that Pauli exclusion principle, we can put 2 electrons into every state. And so this side over here is the volume that our total number of electrons are going to need in K space. And this is that volume of this sort of region in here. And so we can take this and go through and solve for how big our KF has to be. All right, and if we solve for this KF, so first of all, we see that this 8 and the 4 and the 2 cancel. And so if I'm trying to figure out this KF, and so I do that, and this pi will cancel with one of these factors of pi, leaving pi squared. So we get nd pi squared, a factor of 3 from over here. All of this over the volume. And so if I get this guy here, kf, and so I just again find that. So I get 3 nd pi squared over volume, all of this to the 1/3 power. And then you'll see in the textbook, they like to approximate this way as 3 times rho pi to the 1/3 power, where this rho works out to be this conglomeration of nd over volume. Where again this density is the density of free electrons inside your material. It looks like, I forgot a factor of 2 over here, so it should be 3 rho pi squared for that one right there. And so if you recall, our total energy, which we're going to call this special, the Fermi energy, is just going to equal this right here, h bar kf squared. And so if we plug everything in, we get this definition for the Fermi energy. And this here, it's really important. This is the energy of the most energetic electron, energy of the most energetic electron. Right, because if you remember, this vector kf is pointing at sort of at the end of that little pretend sphere we drew, and so the length of kf is all the way at the end, which tells us the electrons that are on the outside that have the most energy. And so that's what this definition here tells us. Okay, so let's move on with this.